Let's look at these water pumping problems. The problems in this subsection all involve pumping water out of various tanks. And for the most part, we do that by lifting the water from the tank, wherever it is inside, up to the top of the tank. And the tricky bit is the water at the bottom has to be lifted higher than the water at the top. So like here, the stuff that's like right on the top, you only have to lift that a short ways. Stuff that's at the bottom has to be lifted the full depth of the tank. So we're going to need to use some calculus to work this out. So let's look at this first example. Suppose you have a tank of water that's 1 meter wide, 3 meters long, 2 meters tall. So this is 3, this is 2, and this is 1. So here's what we're going to do. We're going to cut the water up into like individual slices, like a slice at the bottom and a slice at the top and all in between. Those are going to be analogous to our rectangles that we use for areas, or our discs or washers that we used when we did volumes. So I'm going to put in a slice of water there, and let's see, I guess the water should be blue. I'll color the water in for this first example. So we've got water here for this slice. And we're going to call the thickness of this of course, that's a tiny little thickness, so we're going to call it dx. And x is going to be how far up the water has to move. So what we need to do is figure out two things, force and distance. Well, the distance we've already got. We've got to move the slice up x. And for force, we've got to figure out how much does this slice of water weigh. All right, so to do that, first up, the area of this slice, if we just look at it as a two-dimensional area, it's 3 by 1. So the area of the thing is 3. Its volume is 3dx, because 3 is the area, and multiply that by the thickness, so you get 3dx for the volume. Let me rewrite that a little more legibly. Then we've got to go from volume to weight. Now, this is the first example, so I'm going to do this in 2 steps. But in the future, I'm only going to do it in 1. So to get from volume to weight, first let's go the mass of the slice. To get the mass, you do 3 times 1,000 dx. Now this 1,000 here is this is the mass density of water. One cubic meter of water has a mass of 1,000 kilograms. So that converts it. Let's see. This is in square meters. This is in cubic meters. This now is in kilograms. And then the last thing to do is convert it from mass into newtons, or force. So the weight, we just take that and multiply it by 9.8. And that's going to give us the force in newtons. So let's combine that all together. Let's see, 9.8 times 3 times 1,000, 29,400 dx. That's the weight of the slice, which is what we wanted. Okay, the distance for the slice the slice must be lifted, in this case, is just x, because we have to lift it from wherever the slice is up to the top. And what are the extreme values of that x? Well, at the top, if we think about the very top slice of water, it has to be moved 0, because it's already at the top. And at the bottom, this has to be moved the full depth of the tank. What is the depth of the tank? 2. So the distance slice has to be moved as x, and the x's range from 0 to 2. And so now we've got everything we need to set up an interval. So the total amount of work is the integral of force times distance. Actually, it's worth writing that out. So it's the integral of force times distance. And if you put our force and distance together, distance is x, force is this. Now when we put them together, we need to put that dx at the end. So we just get 29,400 x dx. And our endpoints go from 0 to 2. So it's just a matter of working out that integral, and that'll be the amount of work required. And this is an easy integral. 29,400, divide that by 2, gives me 14,700 x squared from 0 to 2. So if you plug in the 0 and the 2, you get 14,700 times 4, gives me 58,800 joules. Now you can think of that 58,800 joules in a couple of ways. I mean, the way we thought about it for this problem was that's the amount of work required to pump all this water out of the top of the tank. Another interpretation would be, what if you had a what if you had a little hole down here where you could drain the tank out, let it leak out of there? Well, if you think about it, you know, that's when you let it out of there, that's going to release some energy. You could hook that up to a little turbine and maybe make it generate some electricity or something like that. You can pull that energy out of there. And the question is, how much energy is stored in this tank? And the answer is, you know, if the tank is sitting on ground level, you could also think of this as the amount of energy that's stored in that tank by pumping that water up. All right. This is getting long, but I want to do the next example at the same time, or in this video. Because this next example, it says it's the same as the previous one, but with a 2-meter spout on the top. Now, the only thing that would change here, if we drew that same slice in, the only thing that would change is the distance in this case. This is x, and this spout up here is 2 meters, so the distance would be x plus 2 instead of just x. So the work in this case would be, let's see, 29,400. Instead of x, it's going to be times x plus 2. And we're still going from 0 to 2. And tell you what, let's do. Let's get Desmos to do this one for us. Okay, if I put this in, int from 0 to 2 of 29,400 x plus 2 dx, it gives me that for an answer, 176,400 joules. Now, if we go back and compare these two, that's a lot more than the previous one. This is a much bigger amount of energy than that. And that makes good sense because on this example up here, we were pumping the stuff just to the top of the tank. Whereas on this example down here, we're pumping all that stuff up 2 additional meters. So it makes good sense that this is bigger than the other one. All right, we'll pick up in the next video.